Multi-armed bandits is one of the simplest models that allows us to iteratively find an action with the highest reward amongst other candidates. Originally introduced as a way to counter slot machines where people were losing a lot of money, therefore a name of bandit has been given to the model. Now multi-armed bandits could be found in recommendations engines for types of content of all shapes and sizes. So the model itself expects an environment consisting of different concepts. These concepts include a set of actions which are items with which a subject that is interacting with an environment can interact with. So we have a set of actions from 1 to k, where k is also referred as the number of bandits, where bandits could be practically anything from the aforementioned slot machines to movies, books, etc. Since we've touched the topic of rewards, obviously this environment where we operate in, the environment where our multi-armed bandits operate in, expects a reward function which, given the action of some particular bandit, some interaction with particular bandit on the time step t, results into reward corresponding to this bandit on time step t, where t is less or equal to capital T, where capital T, where t is practically the number of training epochs. The environment also needs a Q function or a value function which, given the action of I, the certain time step of t, returns the expected value of returns for a particular item given this action. So basically this function quantifies subject's belief about what reward he should be expecting from particular bandit at a certain time step. This function also determines what action the subject is going to take at a certain time step, since the next I plus 1 is determined by the argmax of the value of the Q function across all actions at time step t. So originally we have k different bandits, which could be slot machines, movies, books, etc. Each bandit has its own rules of assigning a reward, which a predefined reward function through which each bandit passes through is referencing. That means that given the simplest case of a Bernoulli bandit, where we would have a probability of assigning a reward of 0 and 1, and each bandit would have its own unique probability of doing so. These rewards, with respect to unique distributions inside each bandit, are unknown to us. Hence, we need some iterative algorithm to compare our beliefs with what the reward function has given us with respect to each bandit. And the thing that we have received from this function are individual rewards corresponding to each bandit. Now the main component, of course, of this system is the user, or as we referenced him in the beginning, the subject who interacts with this environment. As mentioned above, one of the main components of the environment is the queue function, which generates the expected reward. This queue function generates a vector of scalar q values, approximations of the expected reward for each and every bandit on a certain time step of t. And having calculated these values, we're able to obtain an index of the most optimal bandit that is most likely to generate us a good reward. Now, having obtained a vector of different rewards from every bandit and an index of the bandit from which we expect the highest reward, we combine these steps and pick a certain reward at time step t. Given the argument of the maximum q value and all possible rewards. Given this reward, we are updating our q values and we are tuning our q function to bring our approximation as closer to the real expected reward as possible. So the way we utilize this reward and update our q function accordingly is defined by an additional algorithm which is responsible for how we update our whole batch of parameters in general. Now, having defined all of this scheme, we are missing an iterative loop. After having obtained a reward and updated the q function, we are going right back to our original subject and check in with him if the current time step of t in fact falls behind the capital T. And if it does, we continue our sequence. In fact, I think it is better for us to write algorithm below the update operation. On each time step, we can also keep a sanity check on our algorithm by calculating a regret, which is a difference between the decision made by our algorithm, which can be quantified as passing the picked action at time step of t into the reward function, and we calculate this difference between this term and the most optimal decision that we presumably know across all hidden distributions inside each unique bandit. That would mean that we'll have access to these distributions, and this would basically mean finding the maximum across all expected rewards across all hidden distributions to which we have access to. And hence the regret could be calculated as the difference between these two terms. Having calculated a regret at a certain time step of t, we can plot a cumulative sum of regrets with respect to time steps, and in the best scenario it should look something like this. This would mean that with more interactions our subject makes with the environment, the more optimal our algorithm becomes, and less of an optimal decision he makes on each of the following time step. In the case of us building an algorithm in a wrong way, it would look linear. As mentioned previously, the most trivial of all bandits there are is the Bernoulli bandit. The Bernoulli bandit assigns a reward of 1 based on the probability theta and 0 otherwise. So Bernoulli bandit has a reward function that assigns 1 with probability theta and 0 otherwise. In slot machines, this could be win or lose scenario, and in movies, this could describe clicking or scrolling past a certain recommendation. More complex bandits, of course, entail more complex distributions, which define the reward a person might get. More emphasis, however, should be put on algorithms that could help find an optimal bandit that returns the highest reward amongst all of them. In this video, I would like to review an eps-greedy algorithm as well as the Thompson sampling algorithm, given the Bernoulli multi-armed bandit. So let's talk about the eps-greedy algorithm first. In the case of this algorithm, the Q function returns a mean reward across all t iterations where the person has picked a particular action a of I. So given an action a of I on the time step of t, this function would return Q value at the time step of t given action a of I, which will equal to the sum from j up to a previous time step of t minus 1 across all rewards where the action was equal to the picked action a of I divided by the number of times this action has been picked up to this point. This complex fraction could be practically defined as the mean of all rewards for a particular action I up to time step t minus 1. Now, recall that originally in every algorithm we have a vector of scalar q values. In our case, q values can be predefined as a set of ones of size k. So at the first time step, of course, having taken an argmax of this vector, will be taking an action randomly. In Python, however, since our implementation is going to be done in Python, we'll be always taking the first action, having predefined a vector like this. After that, we'll be calculating the next q value for this first action in this way, and of course update it. So on the next step, t plus 1, our vector would look, instead of all ones, it would look like that. A reward of 1 on time step 1, and then followed by ones. This vector would be, of course, of the same size. So before going any further, I should also mention that updating our q function and updating our vector of q values would be used interchangeably along the explanation of this algorithm and every other algorithm. Having said that, in practice, we did not really update our q function given this formula. By using this formula, we would need to hold information about histories of these reward values for each unique action where these histories could be of arbitrary size, or we would need to hold some additional metadata that would allow us to differentiate between different rewards. Hence, we need to simplify this notation in the following way. So the q value of some action will leave out the I term, since we don't really need this in order to prove this simplification. This is equal to the sum of rewards divided by the number of operations taken up to the certain point. Now, this could be rewritten as follows. The fraction of 1 over t minus 1 multiplied by reward at the time step t minus 1 plus a sum up to t minus 2. This term can be in fact replaced in the following way. Let's add to this sum a fraction of t minus 2 over t minus 2, where both of these terms cancel each other out, and we'll multiply it by the same sum. You might notice that this term is in fact equal to this one, but on the previous time step of t minus 1. These terms are practically equal to each other, but just on different time steps. Hence, we can rewrite this term altogether as t minus 2 multiplied by the q value at the previous time step given action A. Since this term is equal to the q value on the time step of t, and this is the previous time step. Now we can expand this into a difference between two terms, since this brackets can be expanded as t minus 1 minus 1, and this is just a scalar value, so we can simply multiply the scalar value with two of these terms, which will result into the q value at the previous time step multiplied by t minus 1 minus the q value at the previous time step. To further simplify this notation, we can multiply this term with every other inside of these two brackets. So this could be further simplified to the q value at the previous time step minus, actually we could leave it as plus this fraction 1 over t minus 1 multiplied by the reward at the previous time step minus the q value at the previous time step given action A. So now our current approximation of the next q value for a certain action A depends on just the previous one on the time step t minus 1, and we do not really need to hold any other information about all previous rewards as before or their sum, but just the current reward generated by the bandit at the current time step, because we are generating a q value for the next time step in the future. We would be always looking at the current reward inside an iteration loop. However, in order to add an extra explanation, we also utilize a small parameter called epsilon, which could be equal to, for example, 0.01, and it is being compared to some omega, which is picked from the uniform distribution on the segment 0, 1, and based on this comparison, we are either picking a bandit randomly, so we are either picking it randomly from the first bandit up to k, if in fact our omega is less or equal to epsilon, or we are in fact picking it the regular way by putting the q values of all actions into the argmax function. Now let's head over to Thompson sampling. The main idea of Thompson sampling is the fact that we are actively using the conjugate pair of beta and Bernoulli distributions. So we have a conjugate pair of Bernoulli and beta. But what is the conjugate pair exactly, and how does it work in the scope of the algorithm for solving the multi-armed bandit problem? Well, let's look at the example. In the case of the Bernoulli distribution, which is simply a case of the binomial distribution, but for sample size n of 1, we want to find the distribution of original parameters, which would be parameters inside each unique bandit, given the d, we'll get back to d later on, which, given the bias theorem, can be defined as the probability of theta multiplied by the probability of d, which stands for data, given theta, divided by the probability of d. So what is d exactly in our case? D is actually the history of rewards up to time step of t. Probability of d is the probability of us actually obtaining this unique history of rewards, which is quite difficult to calculate if you have already looked at Bayesian probabilistic models, Bayesian statistics in general. People usually dismiss the term in the denominator, the probability of d, because it is unique in its nature and it has many compounding factors inside of it, and it is rather hard to calculate. This is why it is dismissed, and this posterior probability is in fact rewritten as probability of thetas given some data, data being the history of rewards up to the time step of t, is proportional to the probability of theta multiplied by the probability of data given theta. And now, here is where we obtain a pair. But let's look at these two terms in the product more closely. What does they exactly mean to us? But let's look at a simpler term in this product, which is 2. So the term number 2 refers to how likely it is for us to generate observed history of rewards. Commonly, it is referred as likelihood. It could be easily calculated as the product of probabilities. So from I to n and x of I from d. Each of these probabilities are sampled from some Bernoulli distribution or the binomial distribution, considering the independence of an occurrence of each reward. Now, let's take a closer look at the term number one. Number one is called a prior. A prior is the distribution of a parameter which we'd love to know. The whole point of us is finding this distribution and more importantly its mean. So priors are usually a subject of debate, and people could suggest different priors that allow us finding the most accurate approximations for this distribution. However, a very common one for the Bernoulli or binomial rather case is the beta distribution with parameters alpha and beta, and it is rather good for describing thetas. First of all, it is defined on a segment from 0 to 1. And most importantly, its behavior helps us to find really close estimations of thetas. So the distribution curves could look something like this, or even this, or even this. So this framework allows us to curve this distribution as we want to our liking, and this introduces many experiments for different alphas and betas that bring us closer to the real distribution of thetas. Now, let's get back to why this is called a conjugate pair. Now, let's get back to why this product is called a conjugate pair. Let's actually rewrite the probability of finding a distribution of thetas given these as finding the distribution of thetas given some observed x. This changes nothing in terms of how this is displayed apart from replacing d with x. So it turns out that this product, by several simplifications and expansions, can be brought down to another beta distribution. And in fact, this term would follow a beta distribution with parameters of x plus alpha and n minus x plus beta. This means that the whole posterior probability distribution is also following this distribution, and hence a rule of conjugate pairs works. In our case, a rule of the beta plus binomial conjugate pair. So the conjugate pair, which in our case is beta and binomial, which can be found in the product between two distributions, which is proportional to the posterior one, allow us to make assumption about the general family from which distributions regarding the prior and the posterior could be made. Let's take a closer look at what we have written above. particular that the posterior probability follows the beta distribution with such parameters. Recall that alpha and beta are in fact derived from the prior distribution. Of thetas, which follows also the beta distribution with parameters alpha and beta. Recall that x is some observed sample. In our case, x was included in D, which was a history of rewards. So x in our case would be a reward at a previous time step. N would be a number of time steps that we have made up to the point of t, and alphas and betas are picked from the prior distribution. So you can see that we can iteratively tune our parameters of the posterior distribution by adjusting them closer to the real distribution of thetas given the history of observed rewards and the number of steps that we have made along the way. By definition, we want to find the best estimate of Q values that the Q function is based upon that will yield us the best estimate of a reward given an action A of I. In the case of the Bernoulli bandit, that would mean finding the mean, which is also equal to a theta. Well, we also know that this posterior distribution of thetas, given the history of obtained rewards along our iterative process, follows this beta distribution, given the conjugacy between beta and binomial distributions. Well, and combining both of these facts, we can assign a value to the Q function by calculating a mean of the approximated posterior distribution up to the time step of t, which, all things considered, is a beta distribution given the time step t with parameters of alpha at the time step of t, which is defined by x plus alpha at the previous time step, and beta at the time step of t, defined by a number of steps up to the time step of t minus x plus the parameter beta at the previous time step, where x is the reward at the previous time step. Also recall that the mean of an arbitrary beta distribution with alpha equal a and beta equal b is equal to a divided by a plus b. Our Q function should return a fraction for a particular action of I, our Q function for some action I on the time step of t given action of I at the time step of t should return a mean of the beta distribution, which will be equal to reward given an action I and the time step of t plus alpha with respect to bandit I and the previous time step divided by the number of steps up to t minus the reward with respect to the bandit and the time step plus the beta with respect to the bandit and the previous time step. So each bandit would have its set of alphas and betas corresponding to its unique prior distribution of thetas, since each bandit has its own rule of defining a reward. Just like in the eps-greedy algorithm, we're only dependent on the current reward and the previous and previously defined parameters. So just like in the eps-greedy algorithm, we're only dependent on the current reward and previous parameters that we hold for ourselves in memory. So when we pick an action, we refer to posterior distributions that we have built along our iterations in every single bandit. So we have a list of distributions of size k1, since we have k different bandits and each has its own unique posterior distribution. It could look something like this. Or even this. And from each of these posterior distributions, we pick a 1-by-1 sample and we put this new vector of samples from each of these distributions into argmax, and from there we decide which action is the most optimal for us. In fact, this approach in practice yields a better cumulative regret compared to calculating means across all of them. And now let's head over to implementing these algorithms as well as bandits themselves in Python using numpy. So the first step in our implementation is making our examples reproducible to other users. So for that matter, let's import numpy first, then import time, and then set our random seed inside the numpy configuration explicitly by defining it in the seed variable. For that matter, let's assign the number of milliseconds converted to integer and assign this number to seed variable, and set numpy seed to this explicitly defined seed, and also print this seed out. Now, the next step is defining the class for Bernoulli bandit, where B would stand for Bernoulli. Now inside the initialization method, we'll pass in the number of bandits, which by default would be equal to 20, and the initial vector of explicitly defined thetas, which will be responsible for deciding what kind of reward the Bernoulli bandit is going to give upon a certain action. And by default it would be set to none. So now we define our first attribute, which is the number of bandit, and the next one is going to be thetas, which are parameters of unique distributions with respect to each bandit, and this thetas will define the probability of assigning a reward of 1. So by default, we'll generate them randomly from the uniform distribution on the segment 0, 1, and the size of this vector of parameters should be equal to n, since we want each parameter be responsible for forming distribution for each bandit. And of course we define this vector of thetas randomly if probus is indeed none. However, otherwise we assign thetas to explicitly defined probabilities. And the next step is, for good measure, we'll also define the highest theta amongst all thetas, which would be the highest expected reward amongst all distributions. And this will help us to keep sanity check on our algorithm later on. And this will basically define this term here, where we substitute the reward of optimally picked bandit from the maximum expected reward, which we thankfully have access to in these hidden distributions. Now the next step is defining the generate reward method, which will assign ones or zeros depending on what type of theta we have inside the bandit. Now for that matter we'll use the numpy where function, which, depending on the condition of whether a random probability inside the uniform distribution in the segment 0, 1 falls behind the theta, or it falls beyond it. So if it indeed falls behind it, that means that we need to return 1. Otherwise, we return 0. Now let's test this out. Let's create a bandit and generate a reward. Right. Now let's create our first algorithm, which will be the eps-greedy one. Inside the initialization method, we'll pass in the epsilon, of course, which by default should be equal to 0.1, the init, the bandit itself, which will be of type Bernoulli bandit, and the initial probability, which by default would be equal to 1, and this will be our first approximation of of the expected reward. So by default, all bandits would be expected to generate the most optimal reward, and we'll tune these Q values along iterations of the algorithm. And of course, we should set the default value to none, otherwise it will not work. So now let's define our epsilon. This epsilon, assign the bandit attribute, the actual explicitly defined bandit, and the let's initialize our Q values as the as a vector of init probus. Now, the next step is defining a history of rewards and a history of regrets, so that later on we can plot them and see how the algorithm has performed. The next step is defining a set of properties which are read-only attributes. This would be attributes that are not mutable but are addressable. So we'll use these attributes later on for plotting them using matplotlib. So the first one will be a cumulative sum of rewards, which will return a cumulative sum across rewards history. Next one is the same property, but now for the regret history, and we'll call it the regret cumulative sum. Now the next method is of course the predict method. Inside predict method, we will define how this algorithm picks an index of the most optimal bandit. Now, if you remember, we have a certain epsilon parameter, which, depending on whether our randomly picked omega from the uniform distribution falls behind this, we either pick a random bandit from 1 to n, in our case, or we take an argmax of Q values. So this is exactly what we are going to do here. So if our randomly picked omega falls behind the predefined small exploration probability of epsilon, we return a random index from 0 to n excluding n. Otherwise, we return argmax across all Q values. And the next method that we will define here is the update method. The update method will be responsible for updating our Q values, or rather updating our Q function to be as close as possible to generating true expected rewards for each bandit. Now inside this function, the first step is defining an optimal bandit, which will be assigning to the picked bandit variable, and we can get this optimal bandit by just referencing the predict method. then we generate a reward on this optimally picked bandit. And then we log this reward inside our reward history, as well as a regret that we have received. Now, the regret, let's recall it one more time how it is calculated. So we should address the real maximum expected reward across all bandits. So this would mean referencing the attribute that we've defined before of the highest theta, and we should substitute a reward of the bandit that we have deemed most optimal. Now, this would be just substituting from highest theta a real expected reward of our picked bandit. And this would be our regret. Now the next step that is left for us to do is updating our Q function. So we address our vector of Q values. Most importantly, we address our bandit that we have deemed most optimal. And with respect to the formula that we have derived here, we'll update value inside this parameter accordingly. So actually, for that matter, we forgotten to add another attribute, which is n of t, which will hold information about the count of actions that we have made with respect to bandit, with respect to a particular bandit. Now, for that matter, we need to first of all we need to divide 1 over the nt attribute with respect to the picked bandit, which is number of steps that we have made up to picking this bandit again. So this is the number of times a bandit has been picked. And we multiply this fraction by a difference between the reward at the previous time step and the value, the Q value at the previous time step with respect to the same bandit. And then we update our counter by 1. Now that should work. We can specify our bandit one more time. Preliminary defining the epochs constant, or the number of steps, which is t. Then we define our actual algorithm with default parameters. And then we run our training loop for t time steps and update our algorithm inside this iterative loop. Now our algorithm has finished training, and we can now plot our results. Most importantly, we would like to see how well our cumulative sum of regrets actually look like. This will help us to keep a sanity check, as we've explained before. For that matter, let's just plot the attribute reg cumulative sum. Now it looks fairly decent. It's pretty steep at the beginning, but it's plateauing along our iterations. So this is exactly the type of graph that we would like to see. And usually the eps-greedy case is not exactly the most optimal, as we will see with the Thompson sampling algorithm. Now let's code the Thompson sampling algorithm for finding the optimal solution for the multi-armed bandit problem. Inside this algorithm, we'll initialize the bandit, of course, of the same Bernoulli bandit type, and we'll initialize our first approximations of alphas and betas of this distribution that we are trying to approximate to be as close to this distribution of thetas inside each bandit. As soon as we have good enough parameters of alpha and beta of this beta distribution, we will be able to somewhat accurately assume the expected reward with respect to some particular bandit. Now, for that matter, let's define initial alphas as ones and the same for betas. Then we define our bandit attribute. Then we define our alphas parameters. Since each bandit has its own unique beta distribution, therefore it will have a unique set of alphas. This algorithm should have a unique set of alphas and betas. And betas, which we will fill the same way with either initial approximations of alphas or initial approximation of betas. The next step is, of course, defining the same reward history and regret history. And that's about it, what we should define inside of this algorithm. The next step is, of course, defining the same set of properties and then the predict method that will return randomly picked one by one sample from all of these unique distributions with respect to a particularly picked bandit. So for that matter, we'll address to random.beta method, where we pass in a vector of alphas and a vector of betas and a size of these generated vector of one by one samples should be equal to the number of bandits, of course. So we should also explicitly set it to the number of bandits. And given these one by one samples, we should take argmax across all of them. Now the next step is actually the same of updating our algorithm, just like an eps-greedy algorithm, where first of all we pick a bandit by addressing the predict method. Then we generate a reward for the particular bandit. After that, we, of course, keep track of rewards and regrets. And then we update our alphas and betas with respect to our picked bandit, of course. Just as we want over here. Just as the conjugate pair of binomial and beta distributions allow us to. So for alphas, this would be just adding an additional reward at the previous time step, and for betas, this would be adding an extra 1 and subtracting a reward at the previous time step. Now we can see it right here. So we keep track of time steps that we have made up to t. We subtract a reward and add a value of the previous parameter beta at the previous time step. That is exactly what we do here. So we add another time step to keep track of time step inside of these beta. We subtract a reward at the previous time step and we add it to the previous value of the beta parameter with respect to the picked bandit. Now we're pretty much done here, so the only thing that is left for us to do is to initialize our algorithm. We'll actually use the same bandit as before with the eps-greedy algorithm, and we'll use the same number of epochs actually. So now the only thing that is left for us to do is starting our iterative loop for epochs for time steps of epochs number, and we update our parameters inside the algorithm accordingly. Now after it's done training, we can do another sanity check on this algorithm by referencing its property of cumulative sum across regrets. And you can see that the training is far more stable, and in fact if we run it on even more epochs, we'll see that it's finding the most optimal algorithm really well.